Okay, Unit 2 Mechanics, Competency Level 2.7, Hydrostatics. First of all, let's talk about density. So when we are talking about density, let's take an example. We are taking 50 milliliters of water and 50 milliliters of mercury to equal two equal measuring cylinders. And these measuring cylinders, if you check for the weight of these two measuring cylinders, you can obviously see that the measuring cylinder with mercury is more heavier. So you have taken the same volume, but you know that with the volume, mass or the weight of the fluid will be increased if you increase the volume. But you have kept the volume constant and taken the weight. So you can see the mercury is more heavier. But if you have think of another planet, if you are on another planet, the gravitational acceleration would be changed. It will be something else. So depending on the place, gravitational acceleration changes. But what if you have taken mass into consideration? So density can be defined with the help of mass and volume. So density rho is equals to mass m divided by volume v. So this is the equation we are going to use. Rho is a Greek letter. I think you are aware about that. So density is equals to mass over volume. And what's the unit? Unit is kilograms per cubic meter. Kilograms per cubic meter. Then let's talk about relative density. Relative density of a material is referred to as the density of that material compared to the density of water at 4 degrees Celsius and 1 atm pressure. So these are the conditions we are taking in the reference medium. So here we are using water as the reference, and there are some conditions. So you can understand when we change the temperature, density of any material would be changed, and pressure also dependent on the density. So we have to keep these two physical quantities at a certain constant value when we are defining the density. So water has 1000 kilograms per cubic meter density at 4 degrees Celsius and 1 atm pressure. So we can define relative density as density of the material divided by density of water at 4 degrees Celsius and 1 atm pressure. So we can write down that relative density with the symbols as rho of the material divided by rho of water. Then if we have taken the equation as m divided by v for density, so this is the density of the material and this is the density of water. Then if you have selected a certain volume of the material, let's take it as V, and if you have selected the same volume of water at 4 degrees Celsius and 1 atm pressure, so this V will equal to VW. V will be equals to VW. So in that situation, you can write it down as M, the mass of the material, a certain volume, a mass of a certain volume of the material divided by mass of similar volume of water at 4 degrees Celsius and 1 atm pressure. So this is also applicable when you find the relative density. Then density of water 4 degrees Celsius at and 1 atm pressure. I have given you this number before, that is 1000 kilograms per cubic meter. And how about the unit conversion? 1 grams per cubic centimeter is equals to 1000 kilograms per cubic meter. This unit conversion you have to remember. Okay, so I hope you are clear. Please take down notes and let's proceed. Right, here they have given in your resource book some of the materials, some of the liquids and gases which are having their density at 1 atm pressure and 4 degrees Celsius temperature. Usually when we increase the pressure and density will increase. When we increase the pressure, the density will increase, as well as when we increase the temperature in the constant volume, again the density increases. So if you increase the temperature, usually the volume rises. Due to increasement of volume, the density goes down. The density of fluid changes according to temperature and pressure. Generally, the density decreases with increase in temperature. What the reason for this? That is increasement of volume. When volume increased, the mass remained constant, but the density goes down because volume increment. But it is not all the time. So we have to talk about anomalous expansion as well. But here, during this discussion of hydrostatics, we are not going to discuss that. But under thermal physics, we are going to discuss that as well. So in this table, we will compare the liquids and gases. They are having different densities. So maximum density containing liquid is mercury. It is a heavy liquid. It is a metal. 13,600 kilograms per cubic meter is the density of mercury at 4 degrees Celsius and 1 atm pressure. Glycerine, 1,230. Milk, 1,030. Seawater, similar. Water is having 1,000 kilograms per cubic meter. Coconut oil, 800. Alcohol, 800. Right. In contrast, when we have a look at oxygen, normal average air, and nitrogen, they are having relatively very small density. So around 1 to 1.5 kilograms per cubic meter. Helium and hydrogen even less, having less density. Right. So this is there in your resource book. So you can refer to that. Page number 96. Okay, let's proceed. When you talk about fluids, fluids are matter that can flow. When we have a look at what kind of matter are they, mainly gases and liquids are considered as fluids, but solid like sand sometimes can behave as fluids. Usually the density of a fluid increases with increasing pressure. But our study in this field is only confined to the incompressible fluids. Let's have a look at what are homogeneous and incompressible fluids. So these conditions are necessary when we are doing calculations, when we are studying behavior of fluids. Homogeneous fluid is a pure substance or a mixture which is in fluid state and has same density throughout its volume. Okay, so let's take an example. You have taken pure water. So everywhere you are getting the same density. If you have taken an orange juice, if it is a homogeneous mixture, everywhere at the top, bottom, or middle, you should have the same density. If you have taken a kind of a soil mixture, it could not be taken as a homogeneous mixture, homogeneous fluid. When soil try to dissolve in water, it will not dissolve completely. Some of the gravels will settle down at the bottom. Some clay particles are still in the middle. Sand also eventually settle down. So this kind of mixture cannot be taken as homogeneous. I hope you understood the contrast. Incompressible fluids. So incompressible fluid has a constant density at a given temperature and resistant to change its volume when a pressure is applied. When we have applied a pressure, if its volume is not changing, we call that kind of liquid as an incompressible liquid, or we can generalize it to any kind of fluid which is not compressible. So it is incompressible fluid. Okay, pause the video and please note down these. Okay, let's talk about some other physical quantity which we are coming under hydrostatics. That is hydrostatic pressure. So pressure, so even in your previous classes you have gone through, pressure is force divided by area. Force divided by area, or how much force applied per unit cross-sectional area is pressure. Usually measured in pascals, or as you can see in the equation, force measured in newtons, area measured in square meters, so it should be newtons per square meter. So these two units are the same. We have given a special name for newtons per square meter, this unit, as pascals. If you consider the SI base unit, you have to take the SI base units of Newton, and once you have simplified that, you will end up with kilograms per meter per second squared. This is the base unit equivalent of hydrostatic pressure, Pascal. Unit is Pascal. Okay. And pressure is a scalar quantity. So pressure acts in each and every direction in the same time. So we cannot point out a single direction. But in contrast, force is a vector. So if you have taken the cross multiplication, the pressure and the area, we will get a force. Definitely, force has a direction that is always perpendicular to the cross-sectional area or surface area we are considering. Right? Okay. So let's take this example. When you bubble inside a liquid, those bubbles will come towards the interface or the surface. When they're coming out, their volume expands. So here, this bubble was here with this small volume. This big bubble here was here a certain period ago as a small bubble. But when it rise up, it expands. What's the reason? A volume will volume will increase due to two reasons. First one, temperature can be increased. When temperature rises, volume expands, But we know that in this kind of setup, temperature change should not be that much considerable, right? So this is a kind of a same temperature situation. So temperature should not be the reason to volume expansion. Then what? That is pressure. So if the hydrostatic pressure is lesser, it will expand. So you can have an idea that hydrostatic pressure has been reduced when this bubble comes up, right? So the volume expands due to that reason. Okay, what is hydrostatic pressure? That is exerted by a fluid in equilibrium at a given point within the fluid due to the force of gravity. Okay, so this hydrostatic pressure is caused by the force of gravity. So if there is no gravity, there should not be any hydrostatic pressure as well. Let's dig deeper. Hydrostatic pressure increases in proportion to depth measured from the surface. Here, we can identify the surface as the interface as well, because above this surface, it is air. Below, let's assume this liquid as water. So below it is water. So this is the surface, or we can take it as the interface. Right. So the pressure increases in proportion to the depth measured from the surface. This is the surface. Because of the increasing weight of fluid exerting downward force from the above. Okay, if you have taken a kind of a point like this, above this point, there is a certain water column. That water column is having its own weight. This weight is exerted on this point, a pressure. This is the idea. Okay, let's analyze and try to understand this further. I will just give the equation in advance, but we will talk about this later. We will just go through the equation. Hydrostatic pressure at a point is equals to height from the surface multiplied by density of the liquid or density of the fluid. So these are not only applicable for gases or liquids. So those are general terms for all the fluids. General terms for the fluids. So rho should be taken as the density of the fluid, and g is a gravitational acceleration. Respective units are also displayed in here. When there is atmosphere above the surface or the interface, we can take the pressure exerted at a point below the surface as pi plus h rho g. Pi plus h rho g. The pi we have taken as the atmospheric pressure. So we'll talk about atmospheric pressure as well further. So that is 1 into 10 to the power 5 pascals. 1 into 10 to the power 5 pascals. Okay, please pause the video and write down these notes. Okay, let's talk about pressure and depth from the surface. So this relationship. If you have taken a kind of a column of fluid like this and having cross-sectional area A and height h, so we are going to calculate how much pressure is exerted on the bottom cross-sectional area A. Let's take the weight of the fluid column, that is mg. And what's the mass of this column? That should be the volume of the column multiplied by the density of that particular fluid. So the weight can be written as rho v times g. And what is v? The volume. Volume should be the cross-sectional area times the height. That's the volume. So the weight of the fluid column can be taken as rho A times H times G. And what's the pressure exerted on this cross-sectional area? Let's take the pressure acting on a point on this cross-sectional area as force divided by area. Force should be the weight acting on this surface, that is mg, weight. Rho AHG can be replaced as mg here. And the area is A, so we can simplify it as rho GH. So this is how the hydrostatic pressure equation has been derived. Please take down notes. Right, in here we talk about pressure in liquids. Pressure increases with the depth. So as we have discussed in the previous slide, we understood that rho and G are constants. So the pressure is directly proportional to the height taken from the surface. From the surface, when the height or the depth increase, what will happen? The pressure increase. So you can understand the maximum pressure will be there, maximum hydrostatic pressure will be there at the bottom, since the depth is maximum. So that's why this pressure has been converted into kinetic energy. We will do these kind of calculations when we discuss questions. So this pressure is being calculated into kinetic energy per unit volume, and it has the same unit. If you want, you can just analyze that. So that volume, that kinetic energy takes this volume of water to a higher distance because of higher velocity it gets from here. But less pressure will give less kinetic energy per unit volume, so it will move less distance. So this experiment will explain how the hydrostatic pressure increase with the height. Okay, if you having any questions, please send questions to me regarding this practical, right? Okay, so let's go on to the pressure acts in all directions. So this is the experiment we are doing. So we are making holes in the same horizontal level of a kind of a plastic bag, same horizontal level. So then you can see the direction and the distance moved of these water columns are equals to each other. Why? Pressure acts in all directions. So the directions are different from each other, but the distance moved will be the same. Why? Same horizontal height, sorry, horizontal level. They are in the same horizontal level, and they are having the same kinetic energy per unit volume, and their heights are same since they are in the same horizontal level, but they are having different directions. So you can show that the pressure acts in all directions. If you have inserted another hole in here, it will be ejecting water in this direction. So the direction will be depend on the place which we have inserted the hole. Okay, if you want, you can copy it out. Let's talk about characteristics of pressure in liquids. Pressure of a point in a liquid is same in every direction. This is important. So if you have taken a pressure of a point inside a liquid, that pressure is same in each and every direction. Pressure acts perpendicular to a given surface area. So if you have selected the surface area inside the fluid, pressure is perpendicular to that, because the definition of pressure is force divided by perpendicular area. So due to that, the pressure acts perpendicular to given. So actually, it is not the pressure. The force acts perpendicular to the surface area all the time. So pressure has no direction, but the force acting by this pressure. I'll take it as force. Force acts perpendicular to a given surface area all the time. Okay. Pressure of points in a liquid at the same horizontal level are the same. We have done a kind of an experiment as well before to prove that. If there is a pressure difference in two places which is at the same horizontal level of the liquid, it flows according to the pressure gradient. That means high pressure to low pressure. Liquid flows from high pressure to low pressure. It is not from higher volume to less volume, right? If you have taken a water tank, let's say a kind of a fish tank, from fish tank, if you have connected it to a kind of a very small jug, you have to create a pressure difference to take water from the tank to the jug. If you have placed the jug above in a kind of a higher elevation than the fish tank, water will not come to the fish tank if you have connected both the containers, because pressure of fish tank is lesser than pressure of the jug. So then jug will flow water to the fish tank. Even though fish tank has great amount of volume, water flow or any kind of fluid flow, not according to the volume gradient, but the pressure gradient. We have to understand that. Sometimes pressure is directly proportional to the height from the surface. So sometimes we can take liquids in particular, but sometimes we can take gases as well. Fluids flow according to the height gradient, as pressure gradient is directly proportional to the height gradient. Right. Pressure increases with the depth from the surface. We have discussed about this as well and derived an equation as well. Pressure of liquid doesn't depend on the shape of the container. Even though if you have taken different shapes of containers, they will be having the same pressure at the same horizontal level. Okay, so let's take down notes. Okay, I have taken this from the resource book, Atmospheric Pressure. The atmosphere exists a large height from the Earth's surface, several kilometers. So we can take several hundreds of kilometers. The density, but you might argue that it's only for 6 kilometers or something, but oxygen is there up until a certain level, right? But atmosphere is existing for a large height from the Earth's surface. Okay, right. The density of the air in the atmosphere gradually decreases with the increase of height. So you might wondering why it is so. So the same principle we have discussed about the height and density comparison, right? So we have gone through in second. Yeah. So here, when height increases from the surface, pressure increased, right? So similar to that, we can understand in the atmosphere as well. if you have taken the outermost layer of the atmosphere as the surface, so with the height, density increases. That means mean sea level has the highest density. If you have gone deeper, sometimes density increase, right? So when you are going, starting from the surface, when you are going down through the atmosphere, density of the atmosphere increases. But if you have started from the surface of the earth and go up, the density of the atmosphere gradually decreases. You can understand that, right? Any object in the environment is acted upon by a pressure due to the weight of the air above it, right? So you might be wondering why astronauts are wearing that kind of very bulky suit, right? So actually that is providing pressure, atmospheric pressure. We are here in 10 to the power 5 Pascal pressure. That is the atmospheric pressure. Our bodies are adapted to that. But in the space, we don't have that pressure. So the spacesuit should provide this pressure to the bodies of the astronauts. There are some other purposes for those suits, but that is one of the purposes of having those spacesuits. Right. This pressure is atmospheric pressure. The atmospheric pressure gradually decreases upwards from the sea level at a height of about 5,600 meters above the sea level. The atmospheric pressure is about half of the pressure at the sea level. That means 5.6 kilometers above, the atmospheric pressure is becoming half of the atmospheric pressure at the sea level. Right. Okay, so I think you can write down it as atmosphere, the topic as the atmospheric pressure, and one atmosphere is equal to 1 into 10 to the power 5 pascals. And 1 bar is also 1 into 10 to the power 5 pascals. So 1 atm is equal to 1 bar. Okay. Then let's move on to the Mercury barometer. And this is a measure of, this is an instrument to measure the atmospheric pressure. A barometer is made out of one enclosed transparent tube like this, around 1 meter long, filled with mercury and dip in a mercury container from its open end without letting air bubbles to get in. Then when we keep it like this, it will become equilibrium at a certain height. When the atmospheric pressure is exerted on the container, that will be balanced by the height of this mercury column. So we can measure the atmospheric pressure by this height of the mercury column. Atmospheric pressure is acting on the mercury surface. Here you can see that, but here it is a vacuum. There's no any air molecules here. So the weight acting on this point of the mercury column is creating a certain pressure here that is equal to the atmospheric pressure. That's why the liquid column is not getting into the container or take some mercury from the container. It is in equilibrium. Why? Because weight of this creates a pressure. That pressure has become equal to the atmospheric pressure. That's why this is in equilibrium. It transmits it to mercury column and holds it. So you can understand the pressure here is holding the mercury column. If it is mean sea level, the length of the mercury column is around 76 centimeters or 760 millimeters. So we can say that atmospheric pressure is equals to 76 centimeter hydrogyre. So the pressure we can calculate with the help of our equation H2G. Height can be taken in meters as 0.76, and the mercury density of mercury as 13,600, and the gravitational acceleration we will take as g. So it will sum up to a pressure of 1 into 10 to the power 5 pascals. So 1 atm is equals to 1 into 10 to the power 5 pascals. 1 bar is the same. And there's another measuring unit. 1 torr is equals to 1 millimeter hydrogyre. If you have taken 1/760th of length, that is created 1 torr of pressure. That is equals to 133.3 pascals. Right? So if you are measuring this height of a different pressure, not the atmospheric pressure, so you can use this conversion. How much pressure is there for 1 millimeter hydrogyre? That is there. So if you have taken, let's suppose 500 millimeters, so you can take how much pressure is there in that particular place. Right. Hope you can understand all this. Please take down notes. Okay. So for the convenience of calculations, the value for the atmospheric pressure is taken as 1 into 10 to the power 5 pascals. However, 760 millimeters hydrogyre is used as atmospheric pressure in many occasions. So you need to do the conversion whenever necessary. Why mercury is being used as the barometer liquid? So due to its high density, this is the major reason. There are some other reasons as well, but this is the major reason. Let's suppose we have used water instead of mercury. Then we would be needed a kind of a liquid column, water column, nearly 10 meters in height. So it is very difficult to handle in such kind of barometer, right? To take the atmospheric pressure. Okay, some other units are also mentioned in your resource book. They are PSI, pounds per square inch, and kilograms per square centimeter. These are also pressure measuring units. You can understand. I hope these two are important points, so you can take down them. Next, I will go through Pascal's principle, a small theory section, but very important. They have asked even several MCQs, and we have used Pascal's principle in some other essay type questions as well. A change in pressure applied to a static, homogeneous, incompressible fluid which is in a closed container is transmitted undiminished to all portions of fluid and the walls of the container. This is called as Pascal's principle. So what are the conditions? Static. So we are talking about hydrostatics here. So we have to take the fluid as static. And homogeneous. Can you remember what homogeneous is? I hope so. Right. And incompressible. So these three conditions has to be satisfied to apply the Pascal's principle. And it should be a closed container. The volume is confined only for this space. So it should be, the volume should be constant because it is incompressible. Even though we apply pressure, volume has not been changed. So volume has to be confined to this environment, this space. And that pressure is transmitted undiminished to all portions of the fluid and the walls of the container. That means the pressure is being given to this piston as well. Both of them are experiencing the same pressure. So if pressure of this piston is equals to the pressure of this piston at the same horizontal level, we can apply pressure on small piston as equals to pressure on large piston. So we can write down the equation: force on the small piston divided by area of the cross section of small piston as equals to that ratio of the large piston. So this is called as Pascal's principle equation. So we can use this equation to determine any unknown area or force. I hope you are clear with this. Please take down notes. Okay, let's talk about the kind of a measuring instrument we use to take the density of the fluid with the help of the hydrostatic pressure. So a U-tube can be used to compare the densities of two invisible liquids. This is important. We cannot use visible liquids to compare densities from the U-tube. So they should be invisible liquids like this, because we are touching the two liquids up. First, insert the liquid which is more dense and insert the other liquid from one of the limbs of the U-tube. So why we would do this? So first we are inserting the more dense liquid, then we take the other liquid, and also we make sure that we are pouring the two liquids from both the limbs. Sorry, one limb at one limb we use for one liquid, because some of the, so if you have poured water here, some of water will be retaining in here. So in order to avoid water being coming out from both the sides, sorry, not water, but the second liquid coming out from the both side, we pour one liquid to one limb and keep it at the bottom, and then we pour the second liquid like this. So the second liquid will be there in one limb only. We should avoid the second liquid. Actually, this one won't come out from both the limbs if you have poured from one limb. Let's suppose you have poured the liquid, let's take it as red and blue. Red liquid first and poured the second liquid, that is blue liquid. So blue liquid is more denser, so it will go down, disturbing the interface of this, and the red liquid may come out from both the limbs A and B. So then it is difficult to take measurements from that kind of setup. That's why we pour the more dense liquid first and go for the less dense liquid. Then heights from the common interface. So you can see the common interface is here. This is the common interface. This is red liquid and this is blue liquid. So this is the common interface. So from the common interface to the surface of each of the liquid has to be taken. So these are the heights we are interested in. So liquid 1, row 1 is having H1 height from the common interface, and the second liquid, row 2, is having H2 from the common interface. When we take the atmospheric pressure as pi, we can write down the two equations as for the pressure of point A as pi plus h1 rho 1 g, and point B pi plus h2 rho 2 g. Since they are in the same horizontal level, we can equalize these two pressure. Pressure at point A as equals to pressure at point B. But you might be arguing that the point B is the interface. So how we can take it as in the same liquid? So up until interface, liquid is there. So we are taking the point B not on the interface, just below the interface. Below means it is inside this liquid, right? Not in the second liquid. It is blue liquid. Okay, so then A and B are in the same horizontal level. Then we can take the two pressure equals to each other. So we can remove pi, the atmospheric pressure, from both sides of the equation, and also the gravitational acceleration will be removed after. Then h1 rho 1 is equals to h2 rho 2. So we can take the density ratio. If you have taken rho 2, okay, so if you have taken the reciprocal of this, rho 2 divided by rho 1, rho 1 you can take as water, then you are taking the relative density, isn't it? Relative density means density of the material. So here we are taking rho 2 as the density, and that rho 2 divided by rho 1 should be relative density. So here we are getting reciprocal of relative density as h2 over h1. So you can see that density ratio is the reciprocal of height ratio. So if density is high, you are getting small height for the equilibrium. If you are getting a bigger height, the density should be lesser. So you can see this relationship is valid in here. Okay, next day we will go through this practical with the help of YouTube. But before that, please copy down these contents.